We're going to be talking about Chapter 10, and this chapter has to do with semiconductor devices. And we first talk about, in this chapter, we talk about diodes. In the next chapter, we talk about transistors. And we just barely talk about them, but we get enough of this idea of what they are that you have a little bit of an idea what you'd be dealing with the idea of semiconductor devices. And we had a lab with a semiconductor. We had a lab with a diode, and hopefully that gave you a little bit of an idea of what the diode is about. But anyway, we're going to talk a little bit about it, and we're going to talk a little bit about the physics of semiconductor devices. So here's a picture of a nucleus and an atom, and then the electrons floating around the atom, and the protons and the neutrons are there in the middle, and that's the nucleus, and then the electrons are in orbits around it. That's the model that we have of an atom. So the electrons flow out like this, and they fly around, and we then can develop from that a periodic chart of the different elements. And this is that picture of the periodic chart, and you can look at it. And you can see the number of protons and the number of electrons. Like hydrogen has 1 of each, helium has 2, lithium has 3, beryllium has 4, boron has 5, carbon has 6, nitrogen has 7, oxygen has 8, fluorine has 9, and this guy over here, Ne, has 10. So we've got the periodic chart, and it basically shows the number of electrons and protons in an atom. Now down here are some ones that have a number of electrons in their outer shell. It's kind of in the middle, and these are the silicon and germanium, and these are the ones that we're going to be looking at, and that's silicon is 14 and germanium is 32. So the energy level is higher the farther away from the nucleus. Electrons orbit at certain distances from the nucleus called shells. An atom has a number of shells that correspond to the number of electrons filling each shell, and the number of maximum electrons in each shell is 2 to 2 times n squared. So where n is the number of the shell. So the first one would be 2, the next one would be 2 times 4 would be 2 times 2 would be 4 times 2 would be 8. So the first one is 2, the next one is 8, the third shell is 18, the fourth shell is 32. So the outer shell is known as a valence shell, and the electrons in the shell are referred to as valence electrons. These are the ones that can be moved. These electrons can be moved from atom to atom and combined with the outer shell of other atoms to form compounds. These electrons can also move from atom to atom and become electrical circuits. Okay, so we're going to be looking at these two, the silicon and germanium. And in silicon, we have the outer shell has 4, and that's exactly half of this shell that has 8. So we basically, in this outer shell, we're halfway to another shell of 8. So they conduct, but not well. Their outer valence band can be combined to form a rather stable outer shell. However, when doped with other semiconductors with either a 3 or a 5 outer shell, they conduct under certain conditions. Other materials can fall into groups that either conduct or don't conduct and are commonly referred to as insulators or conductors. Insulators do not conduct electrical current under normal circumstances, and conductors do conduct. Materials such as rubber or plastic or glass are good insulators. Materials such as copper, silver, or gold are good conductors. Okay, so we got this good insulator is very few. We don't have any in the outer band. A semiconductor, we have some in the outer band. And the good conductor, we just have one or almost one or two in the outer band. So we basically, these are free to go. These are a little bit free to go, but not too much, and these are locked in and not going to go anywhere. So here's the picture of silicon, and here's the picture of germanium. And again, they've got 4 in the outer band. The 4 adjacent, okay, the silicon atoms bond with each atom in a rectangular shape called a crystal. The 4 adjacent atoms share electrons with the center atom in an arrangement shown below. So this is what we have. We have an arrangement of silicon where they're kind of in a crystalline structure. They're kind of sitting there talking to the one next to them, and they're sharing electrons between them. And that's what a pure silicon looks like. The intrinsic silicon crystal allows some electrons to move up to the conduction band and conduct. When the electrons jump, it creates a vacancy called a hole in the valence band. The electrons in hole form a pair called an electron-hole pair, which can recombine later. Movement of electrons occurs when voltage is applied across the material. Electrons move toward positive end, and this is called electron current. Again, this is the opposite to Ben Franklin current, which is what we typically call is the flow. We would say would be the opposite of electron current, which would be we draw the arrow from plus to minus, and the actual flow of electrons is from minus to plus. Okay, so we have silicon. They can move. They can actually move from one to the other. So if you add a little impurity, the semiconductor can conduct much better. So the impurity is either an atom with 3 or 5. When you add a 3, that's a p-type or a positive type. When you add 5, those are n-type. So you add either a 3 or a 5 to make an impurity on the silicon. The n and p-type semiconductors. To dope a semiconductor, we need an atom with either 3 or 5 electrons in the outer shell to give an extra electron or an extra absence of electron in the outer shell. The atoms with 5 electrons are arsenic, As, phosphorus, P, bismuth, and antimony. Atoms with 3 on the outer shell are boron, B, indium, In, and gallium, Ga. The 5 electron atoms are referred to as N-type dopants, and the 3 electron atoms are referred to as P-type dopants. When inserting in the lattice structure, these atoms create either an extra electron or an extra hole at the point in the structure. The semiconductors that we will discuss all have either P or N or P-type dopants in the structure. So here we have an SB or antimony, and it has an extra electron which it can shear out, and that would give you flow. And here we have one with boron, which has a 3, and that would be a P-type. This would be an N-type. This would be a P-type. This would be this would be a P-type. This would be an N-type. Okay, so the P is positive, and that would be an absence of electron. The N is negative or extra electrons. When we have where they meet, that's called a p-n junction. Remember that the p junction has many holes and the n junction has excess electrons that want to flow over the p-n junction to the other side. If an electron field exists to separate the two regions, there is little flow. This is called a depletion region. If there's an electron field that encourages the flow, that is called a the flow is enhanced and the depletion region is gone. This implies that there is a point at which the barrier collapses, and this is the case. There is referred to as the barrier potential, sometimes called the electron hill. Electrons must overcome to move through the other side of the barrier. So you can remember this term, the electron hill. These electrons have to climb an electron hill, and we'll talk about how much that is. That's a value that you can measure, and you actually can see it. And when you saw that experiment, you actually saw how much that was. So we're going to talk about that in a minute. The other term to describe the current is majority and minority carriers. In P-type material, holes are the majority carrier and N-type electrons are the majority carrier. Remember that the majority carriers in the N region are in the conduction band, while the P-type majority carriers are holes in the valence band. The energy to cross from the N region conduction band to the P region valence band is called the potential barrier. And here it is right here. So you have this energy in the Y direction and this picture of the slice of where the P and N region is, and here's the barrier. So you have to what they call climb the electron hill to go from here to here or from here to here to get to conduct. Excuse me, you have to go from here to here to conduct. This can be measured. It's climbing from here to here. The electrons are measured as for silicon, this is 0.7 volt, and for germanium, 0.3 volts. While silicon is doped with N and P, we can get a lot of different devices. The following are a sampling. Okay, so here are some of the things that we have that are doped with N and P with silicon. The diode, the bipolar junction transistor, this is called the BET, BJT, bipolar junction transistor. Okay, the FET, the field effect transistor, the SCR, silicon controlled rectifier, the phototransistor, an integrated circuit. These are all parts of things that can be attributed to silicon doped with either P or N material. Now we're going to look at diodes a little bit more. The diode is a semiconductor with a sandwich in the middle, with one side of the sandwich P-typed and the other side N-typed. So here we have the picture of a diode. So you've got a P and an N-type material. The P goes with the anode, the N goes with the cathode, and here's the picture of the flow. Now positive flow goes the direction of the arrow from the anode to the cathode. The actual electrons go the opposite direction. The actual electrons are going from the cathode to the anode. So don't be fooled. This is the picture of it. This is the picture, the symbol of it. If you look at it, it's got a little, the diode's got a little band on the one side. This would be like the band of it. You would see the band on the one side. But that's this symbol right here for the little flat symbol. That would be the symbol of how the flow goes. Okay, so that would be our symbol. Okay, so here is when we are forward biased. It's an open door. We've got electron flow. We've got P to N material, and let her rip. This is the way that it goes. When we've got a closed door, it's like this, where you're pulling the electrons away from the P-N junction, and that's like that. Now, this would be an analogy that you might want to think about and having to do with water flow. So you have this a one-way device, and this is similar to the diode. It's a one-way device, and so in the one direction, if you put a flow, you're pushing this way at it. It's not gonna flow because you're pushing against a blocking device here. See that? But if you push the other way, if you push this direction, it will actually the force of the flow will counteract that spring, and it will open that door, and you'll see flow through. So basically, this way is with no flow. This is way with flow. But basically, here's the picture of you're setting this blocking thing up so that it can't go the other way, but it can go this way. The water flow can only go in one direction. Okay. So here's some pictures of different diodes, and the one we have in the lab is a rather small diode, like this one. You can get them bigger. You can get them much bigger than that. And there are two-wire devices. You'll see two wires coming out of them. Somewhere you're only going to see two wires. Okay. So what do you think the bigger ones are used for? Higher current. That's right. They're bigger currents. Okay. So here is a picture of the flow the electrons going across the depletion region and getting that flow. Okay, here's electrons going, here's the holes going. See them steaming into that depletion region? And there it is, the P and the N region. And you also have to always put a resistor in there or else you'll burn it up. In the forward direction, you must add a resistor or your diode will, it doesn't have any resistance at all in the forward direction once you go past 0.7 volts, and it's going to sit there. Now in the depletion, when you reverse the bias, you actually are pulling the electrons away from the electrons and holes away from the depletion region. The depletion region gets quite large, and you basically have no flow. And this way, you're actually going to have no current flow at all. There are times when you can have current in the reverse direction. These are called Zener diodes, and they resist up to a certain point, and then they have what they call a reverse breakdown, and that's why you can have a Zener that will actually will act in the reverse direction. So here's some of the pictures for testing for a diode. Is it working or not? So here is I've got a forward bias, and I've got my diode, and this should flow, and I should get some current through it. I should get some current through it, and then I turn up the voltage, and I should get higher values. So when I'm turning it up until I get to 0.7 volts, very low current. When I get past 0.7 volts, let it rip, it goes pretty high in a hurry. So that 0.7 volts is an interesting point. And here's the graph, and this is the graph that you should have gotten in your lab. It's almost like very high resistance, very low resistance of that diode. So at that 0.7 volts, it's called the knee, and that's where it starts to take off on you, and it becomes very low resistance. And in the reverse direction, there's a knee also, and this is with a Zener. This is an accepted value, but if you have a non-Zener diode and you get past this value, this is the breakdown value, and you do not want to go past that or you'll destroy your diode. Together, the two halves look like this. Okay, in the forward direction and the reverse direction. So now, obviously, we're going to put some pictures here together, and we're going to ask what happens. In this case, we have forward value, and until you get to 0.7 volts, no current. But after 0.7 volts, let her rip. It looks like a short circuit. In other words, it looks like a closed switch. Here, on the other hand, you want the current to go this way, but this resists it, so there is no current flow in the reverse direction until this goes bigger than the breakdown voltage, and at that point in time, this smokes or this goes away. Or in the case of a Zener diode, it goes to 0 ohms, and that's useful as well. So you're looking always to see, is this greater than 0.7 volts in the forward direction, or is it in the reverse direction? Obviously, this is in the forward direction, and it'll never go above 0.7 volts. That's as far as this will go, maybe a little, but not much more than 0.7 volts. Here, you get all the voltage across the diode, none of the voltage across the resistor, because why? Current is 0. And this is called an ideal model. There is no 0.7 volts in this. It's just as if there were no 0.7 volts. You can add the 0.7 volts to your model, and it would look like this. And basically, at this point in time, you'd say, okay, when I get above 0.7 volts, current flows, and that would be the model for it. When I get in the reverse direction, no flow, it acts like an open switch. In the reverse direction, they both act the same, the ideal model and the practical model. In the forward direction, you have to add that 0.7 volts, and I always add that 0.7 volts. It's good to think about it, and it's good to put it in. Okay, so now you can start asking questions for the ideal model, for the practical model. So in this case, what would be for the ideal model for the circuit, find the current. What's the I? What's the current going through here? Well, you got 10 volts, but we don't count this as 0.7 volts. We just say it's 0. So 10 volts divided by 1K is 10 milliamps. In the practical model, on the other hand, you save the 0.7 volts and you actually subtract it. It's 9.3 over 1K, and it's 9.3 milliamps. So the difference is the 0.3 or the 0.7 volts. Here we have, in the reverse direction, the bias, the power supply, and the resistor. Now, you can see that the current would want to go this way, but it can't because it's being blocked. Therefore, there is no current. I equals 0. If I equals 0, the resistance across, or the voltage across the resistor is 0. V equals IR. If I is 0, V is 0. So basically, the voltage across here is 0. So all the voltage here appears across the diode, even though there's no current flowing. It can be confusing, but what's the voltage across the diode? It's the voltage across the supply. Okay, you got to remember that current goes to 0 in the reverse direction. Zener diodes are designed to be operated in either the positive or in the reverse direction. That does not destroy the diode. The Zener diode is designed to be operated in the reverse direction at a value that allows the diode to give a stable voltage across a range of current. The Zener diode is useful to give a reduced voltage in a range. For example, if you need 5 volts but only have 12 volt DC, you can include a Zener diode attached to the circuit to be operated in the reverse direction and rated at 5 volts. The Zener will give a small amount of current at 5 volts for use. You'll need to identify the current level and not exceed that value to operate the Zener in the reverse direction. The value of the voltage is referred to as the PIV, or peak input voltage. Other types of voltage: tunnel diode, varactor diode, Schottky diode, and the LED. The LED is a diode that emits light when forward bias. Like most diodes, when turned on, the LED must be protected for overcurrent with a resistor. However, if pulsed, it can produce more power for a short period of time. LEDs are used in the pulsed form for photo eye applications. So if you have a garage door opener, or have a garage door that has a light that goes across, that if you break a light, the door won't go down. That is a pulsed LED. That's not just a constant light source. That's a pulsed LED source. To forward bias a diode, to which region must the positive terminal be connected? The positive terminal must be connected to the anode or the P region. Okay. Explain why a series resistor is necessary when a diode is forward biased. Well, if you don't have any resistance, I goes to a very large number, and it will burn up the diode. So you need to protect the diode with at least a 1K resistor. Explain how to generate the forward bias portion of the characteristic curve. So how do you generate it? You put the diode in the forward direction, and you put a resistor in series with it, and you start measuring the current as you go up the scale. And you go up in small increments until you get past 1, and you can go up in 1 volt increments after you get to 1 volt. Find the voltage across each diode in the following figure, assuming an ideal diode. And then 6 is assuming a practical diode. So what do you have to do here? Well, you have to find out whether or not, really, what you have to find out is, would current flow in this circuit, which way would current flow if the diode were not there? So you try to picture this without the diode, and this 8 volt supply is bigger than this 5 volt supply by 3 volts. So yes, we would flow this direction, and the diode is against that. The diode is fighting that. So no, there would be no current flow. This would block it. And there would be 0.7, no, there would be all the voltage across this would be the 3 volts, because there would be no current. This overpowers this, so it would try to flow this way, but the diode blocks it. Therefore, there's no current. And the voltage across here is 0. So voltage across here would have to be 3 volts. Voltage running in closed loop has to add to 0. All right, so here is a circuit that if you took the diode out, would there be flow? And yes, there would be flow. It'd be flowing in this direction. So yes, there would be flow. Now, in the ideal, there would be 0 volts across here, and in the practical, there would be 0.7 volts across here. So what would be the voltage across here? Well, let's say 0.7 volts. So what's the voltage across here? 100 minus 0.7, or 99.3 volts. And then you can calculate the current. You can figure out the current of the whole circuit. There you go. This is a little harder, but in this case, if you had flow, would there be flow through this? And the answer is yes. Now, would it be more than 0.7 volts? The answer again is yes. If you combine these two together, that's what? Half of 4.7 is 2.3, 2.35. So I've got a 1K, a 1.5, and a 2.35. So how much of that 2.35 would this eat up? It would eat up about half of it, or about 15 volts. So about 15 volts from here to here, from here to here. And that's enough to turn this on, and it would conduct. So there would be about the 15 volts from here to here, and this would be 0.7 of it, and this would be what's left over. So that would be a way to figure out how much the current is through that one, okay? Find the voltage across each diode, it'd be 0.7 volts here. Here, we have a circuit with two competing supplies. This one would want to go in this direction. This one would want to fight it and go in this direction. Now, which one is bigger? This one is bigger. So this one is going to dominate, and this one is going to not dominate. This is going to be the one that's going to not dominate. So that would be dominated. So we would be actually pushing with 10 volts out of this 20, and 10 volts would be fighting this 10 volts over here. So is 10 volts in this direction enough to turn this on? Oh, you betcha. So the voltage across the diode is plus on the bottom, 0.7, minus on the top. And that's it. Take care. Have a good day.